Have you ever just stopped and wondered, what are you really made of? I mean, what is the screen made of? The air you're breathing? Well, the answer to all of that is atoms. And the story of how we figured that out, it's one of the greatest scientific detective stories ever told. So let's dive into this incredible 2,500-year journey.
It all boils down to this one huge, simple question. I mean, since people could think, we've looked at the world around us and asked, what is all this stuff? What's the fundamental building block of everything?
And finding that answer was, well, it was not a quick thing. It was a complete marathon of thinking and discovering and constantly having to go back to the drawing board. It's a story that spans empires, revolutions, and the birth of science as we know it.
So, our story doesn't kick off in some high-tech lab. Nope. It begins in the mind of a philosopher, way back in ancient Greece. This is where the very first seed of the idea of the atom was planted.
And just look at that time gap. I mean, it's mind-boggling. You've got Democritus in 400 BC, and then John Dalton in 1803. For over 2,000 years, the atom was just an idea. It was a cool concept from a philosopher, but science couldn't even begin to touch it.
So this philosopher, Democritus, he had this thought experiment. He figured if you just kept cutting something in half, over and over, you'd eventually get to a point where you just couldn't cut it anymore. And that final, uncuttable piece, he called it atomos, which literally means uncuttable. He pictured them as these solid, eternal little particles that came in all different shapes and sizes to make up everything we see. It was a really brilliant idea, just pure logic. But with no way to test it, it stayed a philosophy for a very, very long time.
Okay, so let's fast forward, and I mean really fast forward, all the way to the 1800s. An English chemist named John Dalton comes along, dusts off this ancient idea, and finally turns it into a real scientific tool.
For Dalton, the atom was super simple, solid, and totally predictable. The best way to picture what he was thinking is just to imagine a tiny, indestructible billiard ball, a perfect little sphere, and that's the basic building block of everything.
And Dalton's theory wasn't just a picture, it came with some really clear rules. It said all matter is made of these atoms. All atoms of one element are identical, they combine in simple ratios, and you can't create or destroy them. And suddenly, for the first time, scientists could actually predict how chemicals would react. This was huge. It laid the entire foundation for modern chemistry. The billiard ball model was a massive success, for a while.
But, there's always a but in science, right? If atoms are just these neutral, solid little balls, how do you explain something like static electricity or lightning? That perfect little billiard ball had absolutely no answer for the weird, crackling force of electricity. The model was good, but it was incomplete.
And this is where things get really interesting. To find the answer, scientists realized they had to do something that was supposed to be impossible. They had to look inside the uncuttable atom.
So in the late 1800s, a scientist named Thomson did exactly that. He was working with this thing called a cathode ray tube. It's basically just a glass tube that shoots a beam of energy. And with it, he discovered the electron. This little particle was way smaller than an atom and had a negative charge. All of a sudden, the uncuttable atom wasn't uncuttable anymore. It had parts. And this tiny discovery, this little electron, would eventually pave the way for, well, almost everything in our modern world, from TVs to computers.
Okay, so Thomson needed a new model to fit his discovery, right? What he came up with is famously called the plum pudding model. Just picture a ball of positively charged dough, or pudding, with these little negative electrons scattered all through it, like raisins. It was a neat way to explain how atoms could be neutral overall, but still have these charged particles inside.
But you know how science is, right? It never just stops. One of Thomson's own students, a guy named Ernest Rutherford, decided he was going to test this pudding idea. And his experiment, well, it would change everything again.
The experiment was pretty straightforward. He basically set up a little particle gun that shot tiny positive things called alpha particles at a super, super thin sheet of gold foil. Now, if the plum pudding model was right, those little particles should have just sailed right on through the soft pudding. And yeah, most of them did. But, and this is the crazy part, every once in a while, one of them would bounce almost straight back. Rutherford later said it was as incredible as if you fired a 15-inch cannonball at a piece of tissue paper and it came back and hit you. Just wild.
So this totally bizarre result could only mean one thing. The positive charge in the atom wasn't spread out like some soft pudding. No, it had to be concentrated in an incredibly tiny, super dense little core right at the center. He called it the nucleus. And the rest of the atom? It was almost entirely empty space.
This was a complete game changer. I mean, we went from thinking of the atom as a solid blob of pudding to this new picture of a miniature solar system, a tiny, heavy nucleus with vast amounts of empty space around it. The whole picture of the atom was turned on its head by one single, brilliant experiment.
But believe it or not, the story was far from over. In fact, it was about to get a whole lot weirder. As we started to zoom in closer on the atom, the normal rules of physics just started to break down. We were entering the strange world of quantum mechanics.
So first up, a scientist named Niels Bohr came along and tried to tidy up Rutherford's model. He suggested that electrons weren't just whizzing around randomly. They were locked into specific orbits, or energy levels, kind of like planets orbiting the sun. They could jump between these levels, but they couldn't exist anywhere in between. This explained a lot, but it was still a little too neat, a little too simple.
Because here's the final, truly mind-bending twist in our story. It turns out that electrons aren't just little balls flying around a nucleus. Experiments started to show that they act like both particles and waves at the same time. I mean, just think about that for a second. It's like something being a solid rock and a ripple in a pond all at once. This completely shatters the whole planet idea, because a wave doesn't have one single precise location.
And that brings us to where we are today, the wave mechanical model, or the quantum model. In this view, we stop talking about definite orbits and we start talking about orbitals. Now, an orbital isn't a racetrack. It's more like a fuzzy 3D cloud of probability. It's a map that shows us where the electron is most likely to be at any given moment. So we had to trade that comfortable certainty of a little planet on a fixed path for the strange, statistical reality of a probability cloud. And this, I think, is the most beautiful part of this whole story. Dalton's billiard ball wasn't wrong, it was just incomplete. It didn't know about electrons. The plum pudding model wasn't wrong, it just didn't know about the nucleus. That's how science works. It's this amazing process of refining, of building on what came before to get a slightly clearer, slightly more complete picture of how the universe actually works.
So think about that. In 2,500 years, we've gone from a simple, uncuttable dot to a billiard ball, to a plum pudding, to a miniature solar system, and finally to this strange, buzzing cloud of quantum probabilities. It just makes you wonder, as our tools get sharper and our questions get even deeper, what other incredible secrets is the atom still waiting to tell us?